Okay, so in this next section, which is the last section for this unit, we are looking at some physical applications of intervals. So we learned now how to find volumes, how to find surface area, how to find arc length. Now we're going to see some practical or physical applications of intervals. And so the first situation is the situation relating density and mass. So mass of an object is equal to its density multiplied times its volume. So this density situation that we're dealing with assumes that the density throughout the object, throughout the volume, is the same everywhere. Okay, but the reality is that may not be the case in most things. Think about the human body, right? There are parts of your body that are more compact and parts that are not, that are less dense. And so the same with a lot of objects. The uniform density isn't always the case. So now, eventually, if you go on into Calculus 3, you'll be able to talk about density. Actually, you could actually have a density function that actually goes in 3 dimensions or 2 dimensions. For us, though, we're limited to looking at density in a very, very limited sense. So the idea here is we think of objects like either a thin wire, a thin piece of wire, or a thin metal bar. Okay. So either a thin wire or a thin bar, of some substance. Okay. And for these objects, we introduce the density function, which tells us how dense the wire is or the bar is along its length, from a length x equals a to a length x equals b. And the density function we represent using the Greek letter rho. Looks an awful lot like a p, an elongated p. It's the Greek letter rho. So density is the function rho of x. So our task begins, okay, if we have a wire where its density changes as you move along the wire, or a thin piece of metal, where its density changes as you move along the length, then we want to be able to compute the mass of that object. All right, that becomes our task. So to compute the mass, we again think in terms of a thin bar here. We have our thin bar or our piece of metal or a piece of wire. And so just like we did before, we want to subdivide. So we would divide that up into little chunks so that we're looking specifically at the interval x sub I. And so in the interval x sub I minus 1 to x sub I, we would estimate the density as rho of x sub I. Right? We would say for this interval, the density is probably going to be about the same, since it's going to be a small interval, and we're going to eventually let the limit go to infinity. So we estimate it with just the value at that density there. And then we have to take and multiply that by the length of the interval, right? The length of the interval, how much of the wire are we using here? So in this case, our approximate mass for the ith subinterval would be our density function, x sub I star, which is some point in that interval. just some point in the subinterval there, times delta x by the width of the interval. All right, that's our mass step. Okay, and then we would add them all up. We would take the limit and then transform into an integral where the mass of your wire is simply the integral from A to B, the length that you're going along, of your density function integrated with respect to x. Okay, so this is our function, and we can use this to compute the mass of a thin wire, or again a thin metal bar, where its density varies across its length. So, for example, here, let's say we have a thin wire, or again a thin bar or wire, either one. And we know that the density function is rho of x equals 1 plus sine x. And we're measuring along the wire a length between 0 and pi. So 0 and 3.14 inches, meters, whatever the units might have to be. And we want to compute the volume, or compute the mass. Compute the mass. So we would just do the integral from 0 to pi of our density function. And then we just integrate. So integral of 1 is just x. Integral of sine would integrate it as negative. So minus cosine x, evaluate it between 0 and pi. Right, and then we just go in and we compute that. So that's going to be pi minus the cosine of pi minus 0 minus the cosine of 0. So we're going to get pi, cosine of pi is negative 1, so that's going to be plus 1. Cosine of 0 is 1, so minus minus makes it plus another 1. So it turns out this thing has a density of pi plus 2. And so that's really all there is to really say about these kind of problems where you're doing density. It really is just the integral of your function. And by the way, if you're wondering why I used length here, when I told you earlier that density is mass is density times the volume, well, if this is a thin wire, then its volume is really just its length, right? Since we're talking about, again, a thin wire or a thin piece of metal, right? Then it's very small little bar or something like that. Something small, short, then basically its volume is just its length because it doesn't have any thickness to it. And again, when we say a thin bar, we're talking about thin, not very wide. Okay, so something very thin. So its volume is basically its length. And that's why we're multiplying by delta xi there. So we're dealing with stuff where the volume is basically the length. There's no other element to it. So that's why we are multiplying by delta xi there, which eventually means our mass function is just the integral of our density function between our two limits. Okay.